Hi everyone! The purpose of this video is to give you a quick review of the new features in the latest release 20.10 of Isatis.neo. Globally, this new version brings you interface improvements, more data exchange formats, the possibility of exporting or reusing variogram parameters, a tool dedicated to estimation validation, and several new simulation techniques. Let's go to see that. Our first development focus is user experience. It is why we continue to improve the main software interface to enhance your software experience. For example, we've moved the different scene tabs to the top left part of the main view to make them more accessible. We've also added the plus tab to quickly create a new 2D scene, a 3D scene, or a log display. The reporting and messages windows are now fully integrated into the main view and permanently open. A click on the reporting or messages tabs at the top right of the main view lets you quickly access their contents. You can also see that we've made the messages area larger than in the previous versions, where it was at the very bottom of the main interface and less visible. The messages window's behavior depends on whether it displays computation outputs, such as those from statistics, print info, or print variable, or information on the run. In the first case, the messages window automatically pops up if not yet displayed. In the second case, a notification with a counter, message 1, message 2, message 3, etc. informs you that a message has been added to the message window. When you display the content of the messages window, the counter is reset to 0. We've also modified the default color scale, the rainbow one, for a better rendering and less confusion when interpreting a map. We also brought new features to the Exploratory data analysis application. Some of the user complains that they could not load parameters value from already calculated variograms. We addressed this issue and added the load parameters buttons, here for the experimental variogram and here for the model. It opens a new dialog box where you define the geostatistical set from which you want to copy the values. You can see now that the various fields are automatically filled in. The calculation mode, the directions, the lags, the curve type, the cloud parameters for the experimental variogram, the structures, the seals, the ranges, the rotation for the variogram model. If we define a multivariate geostatistical set, we see that a match table pops up. We use it to link the current variable to one of the copied models. Each corresponding variance is displayed for information. You can also activate a normalized seal toggle to rescale the all model variance to the variable variance. You can also export variogram model parameters to a CSV or Excel file. It can be done through the Geostatistical Set Explorer. You see that the menu adds a new export tool. You find it also in the contextual menu. We click the directory path in the messages window to open the Excel file. The table summarizes the different structure, rotation, range, and seal values. By default, the file is created in the public directory of the project. If you select several geostatistical sets, you can export all of them simultaneously in a unique file. If the geostatistical set contains a row and a Gaussian model, parameters are stored in two separate tabs of the Excel file or two files if the output format is CSV. We have also added the H scatter plot to the statistical representation. This graphic enables the spatial continuity analysis of one or more variables. It amounts to a scatter plot between the selected variable and itself and displays the pairs of samples at a given distance from each other and along a given direction. A vector defines this distance and direction. This vector is specified by its orientation and radius with a tolerance on both criteria. The H-scatter plot representation is also available in contact analysis. Because you need to assess the quality of the estimates, we have added the estimation validation tool. It's easy now to verify that the estimates are compatible with the input data statistics. You need first to define the input data at the true values. Here, we choose the iron variable and the corresponding creage data at the interpolated values. Input data can be defined on points or boreholes. Results on regular or irregular grids. You can also define a weight variable and a domain variable. You can add other interpolated data if you wish. It could be creage estimates, but also results of deterministic interpolations, such as inverse distance or nearest neighbor. When clicking Apply, various comparative outputs are displayed. A 3D view, histograms, swath plots, cross plots, and statistics. Each graphic may be customized using the menu bar on the top. As in the EDA, all the graphics are dynamically linked. Our second development focus is innovation, and geostatistical simulations constitute the significant new features of Isatis.neo 2020.10. The latest release brings the performant geostatistical simulation algorithm to the market. SPDE, standing for Stochastic Partial Differential Equation. This new approach is unique and results from a research consortium led by Geovariances and MineSpaceTech and sponsored by 6 major mining companies. The advantages of SPDE method are the use of a unique neighborhood, even if the number of conditioning data is large. The technique can easily digest several hundreds of thousands of data points, so you do not need to worry anymore about the estimation neighborhood size. You can also take into account local anisotropies to refine estimation locally. The computation time is far more reduced compared to the turning simulations already in Isatis.neo. You can obtain simulation realization up to 50 times faster in 2D and 3 times faster in 3D. This version also adds the widely used Sequential Gaussian Simulations, GS. The main advantage of this algorithm, there again, the possibility of using local anisotropies. But computations are slower and simulation results depend on the random path. Isatis.neo also provides you with techniques to simulate categorical variables, more specifically for geological facies modeling. The Plurigaussian Simulations, already available in the previous release, have been developed further and now use vertical proportion curves. The vertical proportions curves or VPC, are used to interpret the lithotype's vertical variability in a deposit. This tool is very useful for geologists as it gives an idea of the original distribution of the facies before deformation. We build these vertical proportion curves with the new proportions modeling functionality. It is a very simple tool which calculates for each level of the working grid the number of occurrences of each facies. The VPCs can be normalized to get a proportion for each lithotype. VPC can be estimated from a categorical variable globally over the area. We select then the option Global Vertical Proportions, or locally over a coarse grid. We select then the option Estimation. We can also define an external constraint as a trend. In an oil reservoir characterization context, this could be the mean proportion of a group of lithotypes over the wall thickness of a layer derived from seismic data. In that case, an innovative SPDE-based algorithm has been integrated to estimate proportions directly. This method is compatible with local geostatistics and can consider local anisotropies. Isatis.neo also proposes multiple point statistics (MPS) with the DC algorithm from the University of Neuchâtel in Switzerland. The approach's principle is to mimic a reference or training image stored on a grid file. This image could be analog if the geological environment is known. You can also start from a simple theoretical image and deform it by defining a rotation and scaling in specific three directions. Check the options rotation and scaling for that. The two other options, proportions and trend, help you build a more elaborate scheme. Check proportions allows forcing out faces to comply with given faces proportions. Checking trend allows defining a trend, for example, to extrapolate mineral properties from a characterized orbit to a similar but different one, for instance. You can also force some grid cells to connect each other, or each simulation realization to fit input anisotropies. DC also applies to multivariate issues. All that makes the DC implementation very flexible. Our third development focus is software interoperability. We've added new import and export interfaces to facilitate further data exchange, in particular between Vulcan from Maptec and Isatis.neo. The new import interface lets you load Vulcan block models, either regular or sub-block, wireframes, and drill holes and composites. On the other side, the grid export tool adds the Vulcan format. It lets you create Vulcan block or sub-block models, respectively, from Isatis.neo regular and irregular grids. Isatis.neo also enables the import of 3D grids in Eclipse GRDECL format. Also improved the loading of borehole data stored in CSV or Excel files. You can now import deviated boreholes with the option One Core Samples file only. It was only available for vertical boreholes in previous versions. You can also now specify the desurveying method used when importing boreholes data as 3 files: assays, colors, and survey When desurveying, we interpolate angles between survey points to compute trajectories at a given discretization step. Several methods are available. The default method, which is the spherical arcs algorithm, the trajectory between two consecutive points in a circular arc. The interpolated azimuth, and dip, which corresponds to the old method. This method is usually very accurate, but is not recommended when a hole becomes close to vertical in between two survey measurements that deviate from vertical. We can help you master these new Isatis.neo functionalities in many ways. Contact us and let's discuss your need together.